Saudi Arabia. He was nominated in 2018 and 19 by Thomson Reuters to be the world's top 1% researcher in engineering. His research findings have been published in 2 books and more than 80 top journals and over 40 proceedings of international conferences. As a co-investigator, he helped to secure UK-India grant of £180,000 funded by British Council to develop the power electronic schemes for a smart microgrid with high penetration of PV generation and electric vehicles, which was started in May 2019. His research interests include operation and control strategies of disease, mathematical modeling and control of optimal energy management system with multi-energy carrier system, and cooperative and non-cooperative game theory application in energy market. Now I request Professor Mousa to deliver his presentation. Professor Mousa, please.
Yeah, thank you so much, Professor Prabhat.
Thank you.
So thank you so much for your introduction. You explain about my previous background. So just a quick explanation, because I need this explanation later when I'm explaining about the project. So as you explained, I did my PhD in University of Catalonia Technology in Barcelona, and under full PhD scholarship from the Catalonian Institute for Energy Research. I did some REPVIM project in this research center, and immediately after graduation, I joined to University of Manchester as a postdoc researcher. I involved in 2 big projects around 4 years in University of Manchester. After that, I joined to Cork Institute of College, and as a senior researcher, and I also involved in the big project, which was a common project between US and Ireland. This is a common project between the one research center in US and in Ireland. And after that, I joined to Northumbria University, and I got some grant. I will explain in this slide. So, as Professor Parvat mentioned, my research interest is about the operation and control strategy for DGs, and let me. Sorry. And mathematical modeling and control of optimal energy management system within multi-energy carrier systems, integration of the different type of the networks, including gas, thermal, electricity, and recently I'm interested to integrate smart transportation systems to the existing electricity network. And here in right hand side, you can see some of grant has been secured by myself. The first one was funded by British Council. It was around £186,000. And recently, in collaboration with one company in Newcastle, I got a grant around £100,000 to support the PhD project. And around 10 days ago, my proposal has been accepted in EPSRC. It was this is a 7 months project, and it has been this is a £70,000 grant, and also I got 2 RDF grant in Northumbria University, and and also one innovative UK proposal also is under review at this moment, where I got positive feedback from reviewers in the first round of the review, and one of QNRF proposal has been accepted around 1 month ago. It is around $600,000, and I'm waiting for another one. Also, we passed the second round. Hopefully, this month it will be clear the result. And I got 2 QU grant, internal grant in Qatar University, and one grant in the KU University. So if I wanted to divide my presentation, you can see in this slide the outline of the presentation. First of all, I will give you the background and motivation regarding the integration systems. What does that mean? What is the application? What is the benefits? And I will show you some simulation, result, and discussion, and I will talk about some of result related to the my previous projects. So, as you can see in this slide, we have integration systems can be shown in this system in this slide. As you can see, in addition to have electricity networks, we have hydrogen, gas, heat, cooling networks, and also, as I mentioned, water network, transportation network also can be integrated to these systems. And for this kind of networks, we have to have utilize some renewable-based technologies such as the CCHP technologies, cooling, combined cooling, heat and power networks, and gas boiler. We need to also we can have a fuel cell, power to gas, gas to power, and some technology related to the electrical vehicle, such as the electrical vehicle to the grid, grid to electrical vehicle, electrical vehicle to electrical vehicle, nowadays to the market, and we can use all of them. But the question is that how we can schedule this kind of the complicated networks, because there are a lot of confliction between these networks. How what is the interaction between the hydrogen system and electricity network, and also gas network? How we can find some of common point between these networks, and what is the complexity of the scheduling in this kind of systems, and how we can manage all of this complexity and scalability. So, in summary, I can say that today's systems are not able to meet future requirements for end users and power producers. So we are trying to use different technologies, and by using of new technologies can help us to increase the power produced by power production, and to reduce the dependency to the conventional systems. And also environmental impact and regulations also can help us to use more this kind of the technologies. So what is the benefit? So,
So, dear participant,
yeah. What is the benefit of the what is the benefit of this kind of systems? As you can see in this slide, we can summarize the benefit of these systems, such as carbon emission reduction, cost of the carbon emission, reduction of the cost reduction of the cost related to the unmet energy or unserved energy. So we will have less interruption in our power supply, and also we can increase the generation and utilization of the renewable based technology. So as a result, we can reduce the capital costs related to the conventional power plant. So, and we don't need to add a new infrastructures related to the new line, transmission line, and so on. And also flexibility in this kind of the systems can be improved a lot, because we will have different type of the technologies, and each of these technologies are consuming different energy carrier. As a result, we will have more flexibility in the systems. In addition, a new opportunity will be created, opportunities related to the retailers for gas network, thermal network, electricity networks. We will have different stakeholders in this kind of networks, and in addition, we can improve the reliability of the system. So if for example, transportation systems can help us to meet a part of our load demand during the on-peak period. So reliability of the systems will be improved. On the other hand, the electrical vehicle can be operated as a energy storage. So we will have a huge number of the electrical vehicle in the future. So these capacities can be used as a mobile energy storage. So we can think about uh, how we can operate these technologies optimally in our systems. And finally, renewable-based technology can create less CO2 emissions, so they can help us to improve our environmental impact. So as you can see in this slide, previously our buildings are only consuming the power. They are just operating as consumers. As you can see, they are just consuming some power from the grid, and we only have one producers who can provide the power for all of the customers. But in the near future, most of the previous customers can be replaced with prosumers. It means these prosumers are able to generate power for us when we have a good weather condition, or for example solar radiation is good, and they can generate some power for us, and we can store the extra power in the energy storage, and when we can restore this energy when needed, for example during the higher electricity price, or when we are in the on-peak period. So as you can see, we have a bidirectional power flow here. It means the polymers can generate power and they can inject to the grid, and they can also consume some power from the grid. So here also sometimes these green buildings, or we call home microgrids, can collaborate with each other in order to help each other to supply their low demand. For example, they can create they can form a coalition between each other, and then they can, for example, if we have extra power in one green building, this extra power can be used to support the shortage power in another green buildings in the neighbor. So on the other hand, we can reduce the power losses because these green buildings are placing very close to each other. So this one can help to reduce the power losses. And forming coalition formation between the green buildings, and sometimes they can make a decision to split out from the coalition when they can feel that working independently can give them more benefit. So we will have a lot of scenarios in this kind of networks. Imagine that in addition to have electricity networks, we will have the thermal, gas, and so on. So you can imagine that the number of the decision variable um, will be increased significantly. And in order to find the solutions to have an optimal power flow in these networks, it will be so critical point of this kind of networks. So one of the objectives for this kind of networks can be to implement the market operator based on transactive energy. I forgot to mention that here we can apply transactive energy, peer-to-peer energy, supply chain, a lot of new concept. And for example, in transactive energy, we can share the power between the players in the networks, considering the privacy of the stakeholders. So this power can be shared between them without sharing so much information. On the other hand, we will have one central controller in the top level, and this central controller should be able to get information from all of players and then make a decision. Later in one slide I will show you. So this is a market operator based on transactive energy. So the stakeholders who are interested to be involved in this framework are such as the home microgrids, the owner of microgrids, home microgrids, or the owner of green buildings, tenants who are living inside these buildings. So we will have two different model of the load demand, including the demand response and critical load. So for each of them, we have to make a new strategy, especially for demand response. We will see how demand can be shifted from one time interval to another time interval, and how much load demand should be shifted, and so on. So, and also we will have distributed system operators, we will have retailers, we will have transmission system operators, and so on. Later, I will show you what is the benefit for each of these players. So, if we want to have to have green buildings in the neighborhood systems, and these green buildings can operate independently, isolated from the grid. So we call these green buildings, or how microgrid can operate in isolated mode, or autonomous mode, or islanded mode, or it can connect it to the grid, and these green buildings can make a negotiation with only retailers and so on. Or another case study is that these green buildings can be operated in collaboration with other green buildings in the neighborhood systems. In addition to have green buildings in this kind of systems, we will have the conventional buildings also. So it means these green buildings can share some power with conventional buildings when they request it, and so here we have to make a framework to have a local electricity market between them, you know. So how this power can be shared, and how much power can be shared, and what is the supply needs, and so on. So how this offer price can be found, and so on. So this is a very simple flow chart regarding to implement market operator based on transactive energy framework. So whereas the our input data is not predictable, for example, we have solar radiation, low demand, wholesale electricity market, or market clearing price, and wind speed, and we have a lot of uncertainty parameters. So first of all, this uncertainty input should send to the uncertainty modeling unit, and here we have to model the uncertainty behavior of our inputs. And after applying the uncertainty modeling, we have a lot of uncertainty methods, such as the Taguchi method, 2-point estimate, 4-point estimate, a lot of things. I don't want to teach something in this presentation. I just want to give you some direction for research. You know, if you are interested, you can go in this direction. You know, if you need any help, also I'm available. I would be so happy to help, you know, if you want. But uncertainty modeling is a big challenges in these activities, and after that this uncertainty parameter will send to the optimization algorithm. So here the optimization algorithm can be based on the different type of methods: heuristic method, optimization method, realistic optimization method, and realistic method, a lot of methods. So for example, partial sum optimization, harmonic search, but there are these methods can be categorized as a heuristic methods, and there is some link here. You can you can go here, and there are a lot of projects based on different heuristic optimization algorithm, Gary Wall's optimizer, wall optimization algorithm, and loan optimizer, and so on. So you can go, for example, to see how this. There are a lot of very good information here, and you can see how this method is working, and also you can access the program code, and then you can use this one. You know, the author is also explained about this method in some very interesting videos. I don't want to go in detail, but I will explain one of them, how this heuristic algorithm is working. For example, if I want to summarize one of the heuristic algorithms, I can explain about the partial sum optimization, but most of these heuristic algorithms are working similar to each other, yeah, and all of them are based on the population, population of the population-based optimization method, inspired by social behavior of animals. For example, flags of birds or fish, wall and so on, wolf and so on. So here, as you can see, in PSO, especially, all of birds are looking for food. They know how far the food is in each iteration, and what is the best strategy to find the food. These two questions is they have to follow, and so we have to define the fitness value, and each of the particles should search in the search space to find the global optima. And for example, we have two equations for in PSO. One, we need to know about the position of the birds in the search space, and we have to define initial value for velocity. And after that, the new value for velocity in the new iteration will be based on this equation. This coefficient factor can change the particle in the search space. We cannot choose a very big value for this coefficient, because particle will move a lot, and after that they will pass the local optima, the global optima, and our algorithm will not find any optimal value. So this is a full chart. In each iteration, we have to change the best and optimal values. And if the optimal values, if for example, if we define the objective function is based on the minimization of the operating cost, if the fitness value cannot be changed anymore, it means we reach to the optimal value. So there is no any solution, and after a few iterations. For example, this is green buildings in the neighborhood systems. We have 3 green buildings or home microgrids. In each green buildings, we have a different technology, as you can see. This is just examples. For example, these green buildings can be a big shopping mall, you can assume. And so there are a lot of different methods to implement the energy management systems. One of method is to have a distributed local energy management systems for each of green buildings, and also we will have a central neighborhood system operators in the top. So each of local energy management systems can locally manage all of these generation units and customers inside the green buildings, and the information such as the excess power or shortage power and supply bids or demand bids will send to the central neighborhood system operator. And in the central neighborhood system operators also we can have another objective function to make a decision how much power can be dispatched from one green buildings to another one, and which one, what is the options. For example, if this green buildings has a extra power, this extra power is better to sell to the which one of these green buildings, or retailers. If this green buildings has a shortage power, so how this shortage power can be provided by green building 2, green building 3, or so on, or even by retailers. So this is a multi-level energy management systems in the neighborhood systems. As you can see, in the green building level, we have several players, producer, customers, prosumers, and prosumers such as energy storage or even demand response. And we have a neighborhood level and also central neighborhood system operators and grid level. So this is one of the purpose flow charts to implement this kind of the energy management systems. As you can see, the most important things to implement the uncertainty modeling, and sometimes I use the forecasting method to predict the power produced by wind turbine and photovoltaic systems. And then in the second stage, we will have the optimization algorithm, and finally we can have we will see how much power should be optimally produced by each of producer, how much power should be optimally consumed by customers. So this is the proposed algorithm in the simple way. So first of all, we have to generate some scenarios in order to implement the uncertainty modeling, and then we have to use the Taguchi method, and finally we have to use optimization method to find the solution. So if I wanted to explain, not in detail, generally for in each stage, first of all we need to get some historical data related to the wind speed or photovoltaic system and so on. So here, as you can see, by using of Renewable Ninja, let me show you. So this is a Renewable Ninja. So you can, for example, you can mention one location, and after that you can search this location here, and this is a solar PV. If you need to know how much power can be produced by solar PV in that area, we will have two database here. One of database is about the European database, and we have a global database. This is related to the last year, and then we can just run this one. So this website can give us the solar radiation data, and here for wind speed also we will have similar things. We can run it, and then for each month we can see how much power can be generated by wind power generation in that area. So for low demands, we need also to some database. So there are some good database. For example, in UK we have a Ofgem database, EDF Energy, and so on. So here, in order to generate the scenarios, we need to have a normal distribution curve. For low demand normal distribution and PV, we will have the normal distribution curve. We need to define a mean value and a standard deviation. For example, at 10 in the morning, our PV can generate, this is a predicted data, 3.3 kilowatt. So we can assume that this value is equal to the mean value, and so we can generate a lot of scenarios for this value. So a lot of scenario can be generated. So this is at 10 a.m. So this is a lot of scenarios based on the mean value is equal to 3.3 and a standard deviation is equal to 0.9. So all of scenarios should be between the inside this curve. So, and after that we need to know what is the probability of these scenarios. So one of the methods can be used to implement the uncertainty modeling is Taguchi method. Taguchi is a scenario based and also inherently is a scenario reduction method. So we need to choose one of these tables. So we have only three uncertainty parameters: wind power, PV, photovoltaic wind power, and load demand. So we can use table 4. So the last columns can be equal to 0. So also for each of these uncertainty parameters, we can have a different level. So if all of them are level 1, or one of them is level 1 and 2 of them is level 2, and so on. So here we can see what does that mean if level is equal to 2. So for example, minimum value of values is equal to the 0.8 kilowatt, and maximum value is equal to 5.2 kilowatt. So the average value is equal to 2.2, and so mean value of 1 is equal to 3.3 plus 0.8 divided by 2, and mean value 2 is equal to 3 plus the maximum value divided by 2. So we will have these two values for level 1 and level 2, and we will have a similar action for the rest of the uncertainty parameters. So after that, by using of this kind of the curve, we need to find the probability of the values. For example, the probability of this value is 1.9 is here, so the probability is equal to 0.0. 726, and the probability of 416 is here, so is equal to 0.3851. So we will have similar things for the rest of the generation unit. Based on these values, we will have the one objective function. So this is the objective function based on all of these values, and after that we have to sort it out, these values based on the minimum value, because this is the objective function is defined based on the minimization of the operating cost. So the minimum value will be the first one, and so after that we can consider this one as a optimal value. And for three green buildings, we have low demand producer, and both low demand customers should be, and production should be matched together. So it means we have to produce power based on the customers. So as you can see, with optimization and without optimization, we have a good difference, and the profit will be increased for each of the green buildings. And also in this green buildings we have a thermal load, so for thermal load also we will have the good profit. So here total consumption power and total generation power has been shown for each of green buildings. Consumption and generation has been matched together. Result related to the energy. If we have energy trading between the green buildings, so we will have this result with optimization and without optimization. The previous table with was about the only the without any energy trading between the green buildings, but here we have energy trading between green buildings. So if we have we compare different optimization algorithms, as you can see, for example, in genetic algorithm here in green building C has a better better solution give us for so the total amount of electrical power generated in green building is more than the rest of the heuristic algorithm. But heuristic algorithms are working in random values. For that reason the maybe we will have different result, but finally the objective function will be very close to each other. If you want to see which method is working properly, so you can compare the objective function. This result related to thermal power purchase from the retailers, so you can see about this. And here in this spider graph, you can see that for example, at each time interval, how much power has been generated by each of these generation units. For example, at 1 o'clock, 81% of the power has been generated by CHP, and 61% of the power has been generated by energy storage, and so on. We don't need, and also a part of power has been bought from the upstream grid. And for example, this one is this scenario is related to the green buildings connected to the upstream grid. So as you can see, In this study, I'm just using the, I'm just comparing the operation of the green buildings, grid connected green buildings or grid connected green buildings in the neighborhood systems. So as you can see, in different optimization algorithms, we have a different pattern for load demand. Here, for example, in harmonic search, by using a harmonic search algorithm, we can see that this amount of load demand should be shifted to this time interval and so on. So you can see, but generally the shifted load should be equal to the dr plus and dr minus. The summation of dr minus and dr plus should be equal at the end of the day. So this one is energy state of charge, energy storage state of charge. As you can see, as you can see, for each of method we have a different um, uh, different behavior for charging and discharging of energy storage. Regarding the market clearing price, as you can see, this is a predicted market clearing price, but as you can see, the market clearing price can be reduced at each time interval by each of these optimization algorithms. And this one is grid connected green buildings in the neighborhood systems. So you can see the load demand after shifting will be changed. The load demand profile, as you can see, we will have the dr plus and dr minus. This is a pattern regarding the charging and discharging of energy storage. As you can see, at the end of the day, for example, here, after 24 hours, as you can see, in green building A, we have we are charging, but in green building B, the energy storage is discharging, and at the end of the day, so the state of charge will be around 70%. It means it can help us to improve the reliability of the system for the next day, because for the next day this energy storage can provide some power if we have a disconnection, unwanted disconnection from the grid. At least a part of our critical load can be supplied by energy storage. So from the different players, as you can see, we will have different objectives. For example, from the owner of the green buildings, they are just looking for to increase the profit, but from the customer's point of view, they are interested to minimize the market clearing price as much as possible. And from the retailers, also profit is very important, so they are looking for to increase the profit. But from the distributed network operators, they are interested to maximize the voltage stability. And from the national grid point of view, they are interested to minimize the congestion or to have a frequency regulation. So all of this energy trading, energy matching, everything should be happen if a frequency regulation and voltage regulation will be kept in the allowable range, So here I wanted to show you some of my previous projects. This is my first postdoc project with University of Manchester corporate project. So in this project, I want to show the responsive load demand programming based on the framework of transactive energy. And so here we want to maximize the total profit of multiple home microgrid systems by taking into account the consideration uncertainties And also I want to show that how these green buildings can participate in the coalition formation, and how we can allocate the profit between them fairly. This is also very important. So I implemented game theory approach, and this is my first case study. It was a research center close to Paris. As you can see, we had three green buildings, green building A, B, and C. In green building A, we had energy storage, wind turbine, CHP, and gas boiler. Green building B, solar thermal panel, electrical heat pump, CHP, gas boiler. And green building C was including 180 um, dormitory buildings, student buildings. So but we only had two generation unit, electrical boiler and thermal energy storage. So here I propose a scheduling algorithm based on the game theory approach for this kind of players. So this is this figure showing us the input data regarding the load demand, electrical load demand, thermal load demand, and market gain price. And this one showing us the characteristics of the generation unit. So this is one of result. As you can see, if each of these green buildings are working independently, the revenue is equal to these values. But when we created dual coalition or triple coalition or grand coalition, we will see that the revenue of each green buildings has been increased. And also we have to follow up the rational things in the game theory based methods. For example, in the game theory, we have to say that each of players should increase the profit, individual profit, and also in the for if we have several players, the summation of the revenue for all of players should be more than the summation of the revenue for each of player independently. So here market clearing price for each of buildings is showing us, as you can see, when we form coalition formation, the market clearing price will be reduced more than when each of them are working independently. And now the next European project was a novel grid project. In this project, I want to propose an innovative solution and tools for distributed system operators in order to provide secure, stable, and robust smart grid. So here we have this is another case study in one village in south of Greece. And as you can see, we have a lot of buildings. We want to see if each buildings are interesting to have a demand response with price or demand response with emission. What will be happen? And as you can see, some of results. So we will have a demand response for each of buildings with price or emissions. And this is another case study in UK. This is 300 buses. It's more complicated, and there are a lot of variables here. And as you can see, we had 11 transformers, and for each of buildings, we will have the load models. Models based on the controllable impedance, constant current, constant power, induction motor, and so on. So all of appliances has been modeled based on these models. So this is a proposed flow chart. As you can see, we have some inputs this input will send to the optimization tools in the GAM software. The objective function was minimize the CO2 emission, minimize the peak shaving, minimize the operating cost, and voltage stability index. And after that, the data will send to the Dix-Island power factory, and in the Dix-Island, the power flow will be down if the voltage stability index is bigger than the voltage stability index of the initial value. So we will go to the next iteration, otherwise we will repeat again this iteration. And after that, this is a credence project with University College Cork, and here I want to see how we can have responsive load demand programming in collaboration with generation scheduling. So how we can have a different type of coalition formation. So this is a proposed flowcharts. First of all, we have to generate some scenarios, and then unit commitment for each harm micro in each scenario will be done, and price-based unit commitment, and then calculating EV and applying the Nikaido-Aizado relaxation algorithm based on the game theory, and finally we will find the profit and market price. So this is our input data related to the wind, load demand, solar radiation, and so on. And this is our output data. As you can see, again, market clearing price has been reduced significantly in the different case studies. So after that, I'm just summarize our project with Professor Ghanim and Professor Prawat and Professor Subati, UK RI project. We had 4 categories: smart charge controller, and then we developed the multi-agent control system, solar PV forecasting, and finally power and energy management systems. So regarding the smart charge controller, actually we propose a fuzzy logic controller, but you know, this is our microgrid in the UK, in our university, including the PV, battery, active load, and electrical vehicle. We had 2 active load, and one of them has been considered as a electrical vehicle. So each of these equipment, we need to get to send some information from each of these equipment to the advanced control systems, and finally these advanced control systems can send a charging strategy for the electrical vehicle and energy storage in order to minimize the degradation cost. So this is a battery management systems, and this is a single leg diagram to implement the fuzzy logic controller for a smart charger for EV. So as you can see from the PV, we need to get a power from the grid. We need to get some information from the electricity tariff and voltage or frequency, and we need to get a set of health from the battery, and so on. But this is related to the fuzzy logic controller. What is how this input will be defined? But as you can see, if we have 3 inputs for simple fuzzy, we need to define 55 rules in total. But if you have 4 inputs, for example, battery state of charge, EV user travel requirements, length of the next journey, travel and weather condition, and so on, plus PV output, we need to define 163 rules. If we have 5 inputs, for example, if electricity tariff can be added, we need to define 487 rules. you can imagine that if we increase the number of the inputs, for example, load, demand, so on, so we need to define a lot of rules. For that reason, um, we implement this flowchart. First of all, we can implement the fuzzy logic controller with only 3 inputs, and then these systems can be these systems can be trained by these 3 inputs, and then the new input can be added to the trained systems instead of to have a new fuzzy logic. For that reason, we can implement this to just to simplify the simplified and reduce the complexity of the algorithm. So this is for various objective function. We implemented this and tested and validated the small charge controller. For example, maximizing the C rate while fulfilling the constraint. This is our objective function. And if maximize profit while fulfilling constraint. And third objective function is about maximizing C rate and profit while fulfilling constraint. Another task was multi-agent controller. So we define each of these asset as a one independent agent. In the multi-agent systems, we are trying to implement real-time operations. So we wanted to have a multi-agent systems to have a self-healing ability. So the simulation has been done for multi-agent systems, and also we had a solar PV forecasting. So some of methods has been implemented for solar PV forecasting, and based on the Newcastle data, we implemented this some of this method and compare some of them with each other, and tested in the network, in the MICROGRID lab. Thank you so much for your attention. Sorry to have a long presentation.
Okay, thank you, sir, for your presentation. Any queries from the participants in?
I try to summarize everything. I just wanted to give you some hint instead of explaining in detail, formulation, a lot of things. I just ignore the equations, formulation, because it will be more complicated, and I cannot explain 2 hours, all of them. But definitely the equation of if you want to mathematically formulate the multi-energy carrier systems, will be so difficult. There are some challenges here. So, but anybody, if you are interested for your master thesis or PhD thesis, I'm so happy to help.
Okay, sir. So thank you for your lecture. So I think from participant end there are no queries. Okay, so if anybody having any doubt or any queries regarding your work, so you can means communicate with Professor
Yes, sure.
Mousa through mail. Okay, so
Yeah,
thank you,
sure.
sir. Thank
Thank
you,
you
sir.
so much.
Giving
Thank you,
your
Professor
valuable time
Mousa.
to us.
Have a good day. See you later.
Actually, very nicely you have presented. You have given many ideas and so many. Its formulation was very nice.
Yeah.
Actually, our,
Thank you
our
so much.
participants get benefited.
There are a lot of works and activities in this area. Actually, I almost summarize. I published 100 journal papers in this area, so I just summarize everything. As I mentioned at the beginning, I don't want to go everything in detail. I just want to give some idea to students to think which activities can be done in this area, you know.
Yes.
Yeah.
Good, good. Very nicely presented. Thank you. Thank you very much, Professor Mousa.
Thank you.
Thank you.
Nice to see you. Thank you. Bye bye.
Thank you. Bye.
Bye bye. Good day, sir.
You too. Bye bye.
Yes.